Alright, so since we're starting Unit 3, you get a new unit objective sheet, and I want to kind of walk you through what's going to be inside of this unit. So, what you can see here is that we have a wide range of topics. You have 5 essential standards and 10 total topics. And this unit is a little bit different from other units because I start us backwards, which means we're going to be working from 310 all the way up to the essential standards. Unit 3 is on electron arrangement and the periodic table. So that means that we're going to first talk about electron arrangement and then talk about the periodic table. And all of your essential standards have to do with the periodic table and how it can be used to talk about electrons. And so it makes sense for us to understand electrons well before we get into the arrangement in the periodic table. This unit covers approximately 3 chapters from your textbook. So we don't follow along exactly in your textbook because I feel like probably none of you want to actually read 3 chapters of your textbook in the next week and a half. Am I right? Okay. Yeah. So that means that we're going to start today by talking about the Bohr model and how it can be supported from the emission spectra of hydrogen. Say what? And in order for us to talk about the Bohr model of electrons and the emission spectrum of hydrogen, we're going to need to talk about light. So while you get out a piece of paper for notes, I'm going to set up some pretty pictures. So, title of these notes are the Bohr model of electrons and light. So the first thing I want you guys to know is that light is energy. And I would like you to consider, can you think of any examples of how light is energy in your everyday life? Kyler. Solar panels, how they use the light. Alright, when you set up a solar panel, you're taking light from the sun, and somehow that must be energy because you're getting energy from it. I think that that's a really great example. Other examples of how light is energy. This is a fun one. So it's dark in here. What do I need to do to make it not dark? Turn on the light. And what must I have in order for turning on a light to work? I must have energy. Right? So you can see that the relationship between light and energy is pretty darn intuitive, isn't it? Ivan?
What's the title of this? I can't read it.
The Bohr model. Alright? Not Bohr like boron, Bohr like
B-O-R-E.
B-O-H-R. And if you're Jimmy, maybe you find it B-O-H-R-I-N-G.
No, I just find it.
Okay. So, what we think of as light is we think of what we can see with our eyes, right? But the light that we can see with our eyes is only a very small part of the light that exists across the whole spectrum of every possible type of light that can exist. What we can see is called visible light because that visible light is what our eyes are able to detect. There's nothing different about visible light from every other type of light except for the fact that our eyes can detect it and transform it into visual images. So when we detect visible light, we can detect regular old white light, or we can detect colors. And the colors of the rainbow go in a certain order. If you like art, you probably know the color order of all of visible light. Starts with red. Does anybody know what comes next?
Red, orange.
Red, orange.
Purple.
Purple comes next?
No.
Yellow.
Orange.
Oh, red, orange, yellow. Look at you guys. It's like you know. Red, orange, yellow.
Green.
Green.
Blue. Indigo. Violet.
Blue. Indigo and violet. Oh, hey, I told you I'm left-handed. Oh no, I didn't. Okay, so here it is, straight up. I'm left-handed. That means I write with this hand, and sometimes it's gonna get in the way of what I'm writing. My head. The person who sat there in the previous class didn't complain.
Well, I'll move it here. Yeah?
It's true. So the only thing that makes this light special is the fact that our eyes can detect it and differentiate it. But it's actually just one type of light, the visible light, on the entire spectrum of light that exists. And that spectrum is the spectrum of light, and it's called the electromagnetic spectrum. I can't spell. Alright, the spectrum is called the electromagnetic spectrum because light is electromagnetic radiation, which is just a very descriptive term for what it is. It's energy, and the type of energy it is an electromagnetic energy. Does anybody know about any other types of energy, potentially electromagnetic energy, or just energy in the form of a wave that maybe you've heard of or we've talked about in class? Different types of waves? Sound. Sound actually happens to not be on the electromagnetic spectrum, but it is a wave and it is energy. So you are right.
Gamma ray.
Gamma rays. Actually, gamma rays are
Microwaves.
a type of energy, and so are microwaves. What else is there, Ian?
Infrared.
Yes.
Oh man.
Ultraviolet.
Does X-ray happen to be one?
X-ray does happen to be one.
Wow. Did I learn this?
Ultralight beam.
Ultraviolet.
X-rays. Anybody else? Can you think of any other type of light that might belong on here? Because there's one more. Anthony?
Is it UV light?
I already got UV light, ultraviolet. Anybody? Can you think of another kind? Poulter? LED light would actually fall under the visible light because it does create a visible radiation. This one, I'm gonna break Olivia's brain. Have you ever heard light? Have any of you ever had the opportunity to hear light? Ethan's got it. What is it?
I was kidding.
Let me ask you this: has anybody ever gotten in a car?
No.
Oh.
No.
Yeah.
Has anybody ever put on a pair of headphones?
No.
Has anybody ever
No.
sent or received a text message?
Vibration. No.
Has anybody ever turned on a television? Has anybody ever been on an airplane?
No.
Yeah.
Does anybody have
Radio.
any idea? Oh, there it is! The last type that fits on here is radio waves. Alright, and radio waves are a gigantic... I'm sorry, I'll zoom it out a little bit. Radio waves are actually a gigantic category, and one of the most important categories in your day-to-day life, because radio waves don't just include AM and FM radio. Radio waves include AM and FM radio, satellite communication, cellular data,
serious.
Data or data?
It's data.
Data and data are both appropriate.
Data.
Data.
Data and data are both correct. Zara.
Is that data?
Radio waves, microwaves, infrared, red, orange, yellow, green, blue, violet, ultraviolet, X-rays, gamma rays. Infrared. Infrared, you probably recognize it as IR radiation, and ultraviolet you probably recognize as UV radiation. So these are all types of light. But we separate them because each of these types of light has a different size of wavelength and has a different frequency or a way that the waves repeat themselves, and they carry different amounts of energy. And so I'm going to start by talking about these in terms of energy, because you are going to see that you probably have experienced some of this. Has anybody ever been cooked to death by radio waves?
Yes.
Yeah, right. Like, I had that experience once.
Well, someone has, but not really.
Hi. In fact, right now, as we speak, everybody in here that has even just one bar of reception, right, that is proof that as we speak, electromagnetic radiation down in this frequency is traveling through your body right this second. Alright? If we turn on a radio, we would get reception, and it would transform that wave into a sound. And that means that right now as we speak, those radiation are traveling around us, through us, in this room as we speak, and nobody here is dead because of it.
No way.
There is not enough energy for that to happen. However, who in here has ever gotten a sunburn?
Me.
Okay, take a look around. We're gonna do a neat little thing.
I'm on the tan.
Look in your group, see if you can find somebody with blue eyes. Here, I'm guilty. Or red hair. Okay. Okay, so blue eyes and red hair are natural blue eyes, natural red hair. Those are indicative of a certain type of genetic code. Alright? And that genetic code is like a messenger that tells your body how much melanin to produce. Right? Melanin is just a pigmentation.
I like watermelon.
Right? Melanin is what causes eyes to be darker colors, the browns, the darker colors, the hazels, the dark greens. Whereas blue eyes are actually a genetic mutation, which means that if you have blue eyes, congratulations, you are an X-Men.
Yeah.
If you have red hair, it is a different type of mutation, but it happens on the exact same gene, the gene that regulates melanin. Melanin is a pigment. Right? So melanin is the material that darkens things. So if you have a darker complexion or darker colored eyes, it means that your body produces more melanin. If you have a lighter complexion and lighter colored eyes, it means your body produces less melanin. And melanin helps block the absorption of electromagnetic radiation, which is why those who produce more melanin have more protection from ultraviolet radiation from the sun, aka they are less subject to sunburn and sun damage. Doesn't make them impervious, it just makes them less susceptible. But I think that by doing this comparison, it's clear to say, does this type of light have more energy in it than radio waves?
Yeah.
You go outside, you get a sunburn.
No.
Right? You've never gone to a radio station and gotten a radio burn. It doesn't work that way. Likewise, microwaves are electromagnetic radiation that can cause molecules to vibrate, and that vibration can cause them to heat up. That's how a microwave works. You put your food in a microwave, you subject it to microwave radiation, it causes all of the polar molecules, aka in your food, the water molecules, to vibrate. That vibration causes the water to heat up, which in turn heats up the food. This is also why certain types of food heat unevenly in the microwave. Something with more water will take more time to heat up, whereas something with less water will take less time to heat up. And that's why if you microwave mashed potatoes and gravy at the same time, your gravy can be so hot it's almost boiling and your mashed potatoes are cold. Okay, so microwaves actually have less energy than infrared waves. And your infrared waves have less energy than all of your visible light. Infrared is what we use to create heat vision or night vision. And if you're a Schwarzenegger fan, this is what Predator sees with. X-ray radiation, remember, that was the original radiation that we detected from uranium ore that allowed us to develop the first mobile unit of X-ray technology, which was used to treat soldiers on the battlefield of World War I. And radiation from gamma rays ultimately is what caused Marie Curie's cells to mutate and resulted in her dying from leukemia. So do you guys notice the pattern?
No.
That as we travel this way on the electromagnetic spectrum, the energy increases? So we can compare that to this light here. We could say that red light has less energy than orange light, and violet light has the most energy. And this goes for flames too. Have you ever seen a fire? Right? And a regular fire at a campfire is just a regular burning orangish, maybe yellowish flame. However, if you get a hotter source, that fire can turn into a white light, or you can even see blue and violet in that light. That means it's a hotter fire. So this energy comes from the fact that each of these lights has a different wavelength. So when I say wavelength, I'm going to give you this symbol lambda. It means wavelength. And wavelength on a wave is the length from crest to crest or from trough to trough. So from the top to the top or the bottom to the bottom. That's a wavelength. Alright, so in a wave, from top to top or bottom to bottom is a wavelength. And the wavelengths actually change, increasing, going this way. So that means the bigger the wave, the smaller the energy. Right? Radio waves, AM radio waves, can be as big as Central Park. That's I forget if it's 3 miles or 3 kilometers across, but big. Right? So big that even an FM radio wave is about the wavelength of the height of a giraffe from ears to hoof. Right? That's how big an FM radio wave is. Microwave is about the size of a coffee bean. Ultraviolet light is smaller than your skin cells, which is why they can go in there and cause so much damage. X-rays are smaller than your DNA, which means that they are very good at causing genetic mutation, which means the X-rays are only a little bit less bad than gamma rays, Right? Overexposure to X-rays can cause cellular mutation, which can result in cancer and death. Gamma rays are so small that they are small enough to penetrate the nucleus of an atom and cause that atom to break apart into nuclear fission. Right? Which means that not only can gamma rays destroy your cells, wreck up your DNA, and cause a very bad day, they can also cause nuclear fission, which causes such a massive release of energy that this is where the concept of characters like the Incredible Hulk and Dr. Manhattan come from. The fact that the manipulation, the energy radiation is so intense that you're not just manipulating things on a cellular level, you're not just manipulating things on the level of DNA, you're manipulating things at an atomic level. So you could turn that into some sort of a superhero fantasy where their actual structures changed so much that now they're an awesome superhero person. But in reality, what that means is that you have so much energy transferred into your body at a cellular level, at a level of DNA, at a level of atomic structure, that all of that energy releases into you dissolving into a big pile of gooey nothing. People who have high levels of X-ray and gamma ray exposure die of radiation sickness.
No cure.
No cure. Okay, so energy and wavelength have an inverse relationship. As energy goes up, wavelength goes down, and that makes sense. It also makes sense that the frequency, right, the frequency also increases with energy because frequency is how many waves per second. Right? So this is how these ones have more energy. They're very small and they repeat very fast. A radio wave, it might take 5 seconds for a radio wave to pass by. However, a gamma ray, you could have literally thousands of gamma rays per second. And that's where all that energy comes from. I'll zoom out. Bro. Gio. Move it up. Like that. Okay. Alright, so this relationship is going to help us understand the experiment that Bohr did that tells us how electrons behave. Remember when we left off with atomic structure, we left off with this idea that electrons are somehow around the nucleus. That's what we know. They're around the nucleus. But that's not very telling. That doesn't help us understand where the electrons are. But Bohr did an experiment, and Bohr told us, hey, I know where the electrons are now. And he created a new model of the atom that included electron structure. And that was really important. And he used the science of light, and he used what we understand this about light in order to do that explanation. So up to this point in time, we've been talking about light energy, and most of us have probably been thinking about the type of light energy that comes from the sun. But it happens that light energy can come from just about anywhere. Have you ever seen a light bulb turn on?
Yeah.
Alright, that's energy released from the substance within the light. Have you ever seen a fire burning? Right? That's energy released from the reaction that caused the fire. And do you guys remember J.J. Thomson's cathode ray experiment? Right? The one that allowed us to know that electrons could be removed from an atom? Alright, well, it just so happens that when electrons gain energy, they can carry it with them and release it. So energy release can come from electrons too. And that's what we're going to take a look at. In fact, we're going to be looking specifically at energy that's released in the form of light from an electron. Alright, so an electron can release energy in the form of light, and if we look at that light through a prism, how many of you have ever seen a rainbow? Have we seen rainbows? Alright, rainbows, those come from light, right? The light goes through a prism. The prism that the light goes through is tiny water particles. And those tiny water particles break up the light into a rainbow. And so when we look at light that's been moved through a prism, we see red, orange, yellow, yep, green, blue, and violet. And we know this relationship, right? Wavelength gets bigger going this way, energy gets bigger going this way, frequency gets bigger going that way. So Bohr wanted to use what we know about light and some peculiar observations that were going on at the time, because we were intensely studying radiation and nuclear chemistry at the time. As a matter of fact, did you know that the microwave, like the very same thing you use to heat up your lunch every single day, or your snacks or whatever comes out of the freezer, that device is a result of intensive research done during the nuclear arms races. We were studying radiation and compounds that created radiation. And by doing that, we discovered that microwaves were a thing, and they were very good at heating things up. And because they weren't incredibly high in energy, it was very easy for us to generate them and harness them. And thus was developed the technology of the microwave oven. And people at the time of the invention of the microwave oven knew that the microwave oven was created as a result of nuclear research. And people knew that nuclear research was a scary thing because they'd seen mushroom clouds. And they knew and they heard about what was happening, and probably by that point in time, Marie Curie had already been buried. And so we knew that radiation was a potentially dangerous thing. We were trying to make an atom bomb. But we made a microwave and then started selling it to people so they could heat up their food. And they knew there was a connection. And so there were a lot of people who feared the microwave. In fact, that's where the term, oh, you need to heat up last night's leftovers, why don't you nuke them? That term comes from the fact that the technology that developed the microwave oven was nuclear technology, and people had a hard time separating microwave radiation from the other types of radiations that cause things to go boom. So, just like the cathode ray tube, if you took a tube full of hydrogen gas, this is my tube full of hydrogen gas, forgive me. It's full of hydrogen gas. And if we took it and we hooked it up to an energy source, here's my energy source, the plus and the minus for a battery. This is excellent art, I'm telling you. Alright, so if we hook it up to a battery, that means energy is going into this tube, correct? Alright, and energy going into the tube gets absorbed by the electrons, just like the electrons in the cathode ray tube were able to absorb energy. And when those electrons release the energy, that energy comes out in the form of light. And this is the light that Bohr wanted to investigate in his experiment with the hydrogen atom. He said, if I could just understand the light that electrons released when they release the energy they absorb, I might be able to understand what they're doing and how they're moving based on the energy that they're absorbing and releasing. But in order for him to do that, he had to separate light by wavelength. So he analyzed the light by looking at it through a prism. And what he expected to see was an entire rainbow of red, orange, yellow, green, blue, indigo, and violet. But what he actually saw instead was only 4 colors and black in between. No color in between. He saw the colors red,
Yellow.
wrong,
Green. Blue.
orange, a tealish color, which is somewhere in the spectrum between green and blue, but we'll call it blue for the sake of simplicity, and violet. That's all he saw. He did not see a whole rainbow of colors. And so he said, oh, that's interesting. Why? What is it about hydrogen when we look at the actual energy that they release? Why can it only release only 4 types of energy that we can see? That was the question that he was going to answer, and he was going to use hydrogen. And the reason he used hydrogen is, how many electrons does hydrogen have?
1.
It has 1 electron. It's much easier to analyze 1 electron at a time than it is to analyze a compound like osmium that has 76. So he chose hydrogen because hydrogen spectrum is a result of 1 electron per atom. Right? So here's what his proposal, his explanation was. And here's where you're going to draw a nice, big, pretty picture, just like me. Are we ready?
Yeah.
All right. So give yourself some space. You're going to draw hydrogen's nucleus, which is just a proton. And then you're going to surround hydrogen's nucleus with, imagine if you will, the nucleus like a little planet in space. And surrounding it are 8 different rings. Okay, 1, 2, 3, 4, 5, 6, 7, 8. That is some nice art I've got right there, isn't it? I could tell you're impressed. Okay. He started with 8-ish, and it was just kind of a starting point. And you're going to think of those 8 rings like steps on a ladder. Okay? So when the electron is comfortable and happy and where it wants to be, we call that place ground state. Alright, so when the electron is down there, where it belongs, without any extra energy, we call it ground state. It's the lowest amount of energy an electron can have. Okay? If we give that electron energy, it will get excited, and depending on how excited it is, it will jump up to another level. So you give it a little energy, it's like, oh,
Don't jump up.
oh. But if that electron wants to give away the energy, it'll go back down to ground state. If you give the electron more energy, it'll go up higher. It'll be like, oh, oh.
You almost fell.
Please be careful.
And if it has to give up that energy, it'll go back down to ground state.
It like falls back down.
Stick.
It'll fall back down, right? It doesn't take any energy. It has to let it go, like the song.
What about the left?
Right? If you give the electron lots of energy,
Get from the front.
Hang on, how's it
it'll go even higher.
How's it up there? How's the
Okay.
weather?
And if it wants to go back down to ground state, it has to
Fall.
What is it?
it has to fall. It has to let it go.
Fall.
And the energy leaves. So that means that you can imagine each of these, what we call them is orbitals, and if you think about the planet analogy, right, the nucleus is a planet and these are rings around the planet. Orbits, or orbitals, is kind of a cool name. It makes sense. So what we're going to do is we're going to take like a thin slice, a little snapshot of what the electron is doing when it gets excited and jumps up and down. Alright, so our little snapshot of our orbitals. This is where people really appreciate my artwork. I know it because my artwork is awesome. Right? You just can't even. Alright, so the bottom one, alright, we called that one ground state. It's on the ground and it's happy there. And then, going up, we can also call that that energy level, which is the same thing. It's what each orbital is. And just because we give it the symbol N, because energy, get it? Energy. Energy. Get it? Alright, so ground state is the lowest it could be, so we call that N equals 1. Then, the next one up would be N equals 2. The next rung on the ladder, the next orbital.
Going out?
Going out from the nucleus. Up, away from the nucleus. And then equals 3. N equals 4. N equals 5. N equals 6, and it keeps going up and up and up, and we'll call the last one, we'll say the last one is N equals infinity. Like, you could be infinity energy levels away.
That's cool.
Okay? If an electron makes it all the way to the top, that just means it got away. That electron left that atom. And it became an ion. Okay, so electrons can absorb energy. Remember, we said we can give an electron energy, so that the electron is hanging out down here at the ground state, nice and relaxed, right? We can give it energy. We can put some energy into it. And when we give it energy, if we give it a little bit of energy, it'll be like, oh! But if we give it more energy, then it could be like, whoa! Woohoo! It just escaped. Alright? So, depending on the size of energy we give it, will determine how high up the ladder it makes it. Sure. Alright, so depending on how much energy we give it, it determines how high up it will jump. And so we can actually give that amount of energy a name. The amount of energy, the bracket, the amount it takes it to go from one level to the next is called a quantum.
Quantum physics.
Yep, that's right. You guys are learning quantum science right now. Alright, just for the vocabulary, and then I'll go back to the box. Okay, so quantum is just the amount of energy that must be absorbed or emitted for an electron to move between orbitals, right? Or between energy levels, right? That's what a quantum is. So if I give an electron a quantum, it will go up exactly that energy level. If I give it a different quantum, it'll go up a different energy level. That's all a quantum is. When I say a quantum, I'm saying a specific amount in between two different energy levels. Come on, guys, my handwriting's not that bad today.
I just blind.
It's pretty darn.
Can you read that one second?
I can't read it.
I never said it too. I'm not good.
Did you read that?
Ivan? Alright, it's the amount of energy that must be absorbed or emitted for an electron to move between orbitals. Ethan, this is your fault.
He's the one that isn't like you.
Yeah, exactly. I feel like maybe you were just projecting onto Jonna.
Who likes bananas? I like it. Banana. Me. Banana.
Huh?
What's the equation up there? Orbital equals
It's just an orbital is what an energy level is, and the symbol is N. Okay, so I'll go back to these guys. So depending on the quantum, right, this is a quantum that would take it from N1 to N2. This is the quantum that would take it from N1 to N6. Right? This is the quantum that would take it from N2 to N5. Right? Each quantum is how much energy it takes it to go up or down an energy level. Alright? So depending on the quantum of energy that the electron gets, it'll jump to a different energy level. Or if it's given too much of a quantum, it'll escape the atom altogether. And it just so happens that in order for the electron to go back down to ground state, it has to give away a quantum of energy that will allow it to go back down to ground state. So if the electron's at N2, it has to give away this amount of energy, exactly that amount. If it's at level 3, it has to give away that quantum of energy. Energy level 4, it has to give away that quantum. Right? And so you're going to see a pattern, right? The energy level between any of those states and energy level number 1 has to be bigger than the energy between 1 and 2. Do you see it? It's either this much energy or more. Right? And so what we say is when we look at the spectrum, we look at what energy gets emitted when we watch hydrogen through its prism. We can't see this because it's too much energy. This is ultraviolet and more. So we say the transfer between n equals 2 and n equals 1 is so big that, spelling is hard, that any transition to ground state back down to n equals 1 has too much energy to see. We can't see it. It's too much energy. When we look on our electromagnetic spectrum, right, we're talking about energy in the ultraviolet region, energy in the X-ray region. That's how much energy the electron has to give away to go back down to ground state. So sorry guys, every time you look at a hydrogen lamp emitting energy, some of that energy is going to be X-ray.
Yes.
too much energy to see. But likewise, the spacing in between 3, 4, 5, and 6 is really, really small. Alright, so if we looked at the spacing between here, 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 alright, those are really small spacing. So we say that to get between n equals 4 and n equals 3 is too small to see. Alright, that means that it's actually going to be infrared or less. Alright, and have you ever noticed that when a light is on for a little bit, it gets kind of warm?
Yeah.
Yeah, that's because some of the energy transfer that's happening in that lamp is infrared instead of visible. Alright, some energy that's released from a light source is too low to see. We only see the visible light, and we can't see the infrared light. Which must mean, if we've talked about what's too big and we've talked about what's too small, that some of the energy transfers must be just right. And the energy transitions that are just right are transitions between all n to n equals 2 are just right to see. Those transitions produce visible light. Between any of the energy levels above and energy level number 2.
D.
Where's what? This?
Wait, do you have notes on there just showing?
This?
Or is it live?
This is live.
What the hell? On the right side.
Oh, those are physics.
I was wondering about
Oh.
Those.
What did they give us? No. We have to do a lot.
So let's take a look at those just right transitions. Back to my beautiful orbitals. Okay. It just happens that the energy transition from energy level 6 all the way down to energy level 2 requires the most energy to be released. So that would be violet light. The energy transition between energy level number 5 and level number 2 is less quantum than 6 to 2. So that produces blue light. And the energy transition between 4 and 2 produces orange light. Which of course means that the least amount of energy released produces the red light. They're the Goldilocks emissions.
Yeah, 1 second. 1 second.
So, you've been troopers. We're looking at, like, I said that this is a quantum. We talked about these energy levels and how an electron can move up and down and what type of light it causes it to produce. And this is high level stuff. So it's okay if you're feeling a little iffy about it. But the big takeaway here that we want to make sure that we feel pretty okie dokie about is if electrons could go wherever they wanted, then they should be able to release any quantum they wanted. Does that make sense? If they could go wherever they wanted, no matter what, they could release any quantum that they pleased. They should be able to release a green quantum and just go hang out in the green level. But they can't. They can only release violet, blue, orange, and red. Which means that there are spaces around the atom that they are not allowed to be in. Electrons cannot be anywhere they want. Just like a person can't stand in between ladder rung number 2 and ladder rung number 3. It's impossible. If you tried to go in between ladder rung number 2 and ladder rung number 3, you would fall. It's the same concept with energy levels and electrons. Electrons can't go in between orbitals. They can only go to the orbitals. There's no existing in between them. Which means that they can only absorb and release quantum that equal these amounts. So we can come up with a general statement that explains what Bohr's experiment with the hydrogen atom tells us about electrons. And that statement is the appearance of these specific, right? The red, orange, blue, and violet Alright, that means that the only reason that this could happen, it can only be explained if those are the only places that electrons can go. So it can only be explained if the electron can only exist in specific orbitals. Right? No going in between the rungs. No going in between the orbitals. They can only be on level 1 or level 2 or level 3. You can't have a 1.5. It's not allowed. Just like you can't stand in between two rungs on a ladder. So bringing it back around, you guys are still copying. I'm going to give you a second. Going to show you 3.10. What? Yeah, you're copying me. I told you to, but you can't use this on a test. Did you know that's why you can't use your notes on a test? It's academic dishonesty. You'd be copying me.
Also, if we took our own notes, can we use them?
No, because you'd be copying me.
No,
You wrote down what I said.
What if we took our own?
You wrote down what I showed you.
What if we,
You wrote down what the book said.
What if we rewrote
Copying.
So if we're answering it right, then you
What if
taught
we rewrote
Okay.
it in our own words? That way it's not copied, so if we used it on the test.
Alright, ladies and gentlemen, I want to make sure that because we are running out of day in the day, I want to make sure that we can answer this question. It says, explain how the Bohr model can be supported from the emission spectra of the hydrogen atom. Well, here it is. The emission spectra of the hydrogen atom allowed us to only see 4 colors. We can only see red, orange, blue, and violet. The only way that could be explained is to say that those are the only energies that the electron can absorb and spit out, which means those are the only place that the electron can go. It can't go anywhere else. That means that Bohr was right. Electrons can only live in orbitals, never outside of them. So if the electrons can only live in certain orbitals, then it explains why we only see certain energy when it goes back and forth between them. This is the answer to Essential Standard 3.10. 310.
What?
3.10.
No, what was the answer?
Trace? I don't know how to say point.
Because we can only see red, orange, blue, and violet light in the hydrogen spectrum, it proves that the electron can only live in certain regions, or it can only exist in specific orbitals, never anywhere else. Electrons. This part or this part? This? Do you have your this?